So thank you all for attending. We're of course here for the thesis proposal defense of Elias. The format that we'll use is, as usual, I'll ask committee members to not pose questions after Elias speaks for 40 or 45 minutes, because we'll have plenty of an opportunity to do that, unless there are no questions, and then we can start asking our questions. The committee is myself and Christos Kastrisios as supervisors. The committee is then Larry Mayer, Xi Shang, and Glenn Rice. Larry unfortunately has something that came up, and so he will not be here, but he is in fact a committee member. So with that, I will turn it over to Elias for a presentation of 40-45 minutes, and then we'll ask questions.
Yeah, thank you, Kim, for the introduction. Thank you, everyone, for joining both online and everyone in person. It's good to see your beautiful faces. Today, I'll be presenting my dissertation proposal, which focuses on developing a unified operational framework for interpolation uncertainty in bathymetry. I'll start by motivating why interpolation uncertainty is important. Then I will outline the 3 chapters of this dissertation, and I'll conclude by some of the scientific contributions of this work. Yeah, it does not always. Okay. As we might all know that about 72% of the world's ocean is unmapped to modern standards, and even with the United States waters too, there is still about 44% of the United States waters unmapped to modern standards. As a result of this, interpolation is typically required amongst these sparse bathymetric data sets to fill in the gaps and create a digital bathymetric model of the seafloor. And that is important for numerous scientific, operational, and commercial applications. There are many examples of data sets for creating digital bathymetric models based on coverage, including complete coverage bathymetric data set, which could be from multibeam echo sounder or single beam echo sounder. Then there could be incomplete coverage bathymetric data set, which could be from set line spacing surveys or historic or sparse data set, usually archive data set. And it is this incomplete coverage bathymetric data set that requires interpolation to fill the gap so that we can create this digital bathymetric model that I'm talking about. However, this interpolation process introduces an inherent uncertainty into the resulting DBMs. DBM, I would say DBMs, but that's digital bathymetric models. I think all of us here, we know what that is. So this interpolation process introduces an inherent uncertainty into the resulting DBM. And as we know, like as any scientific measurement, the uncertainty that comes with this DBM is very important for numerous applications. And I always like to look at this concept, using the Greenaway's tool of hydrography. How deep is it? How well do we know it? And who provided the data? I want to say that, if you know just the depth, that is not sufficient if you don't have the quality of the bathymetry or you don't know the source of the data. So it is important that we have the source, we have these 3 components. So if a leg is missing, what happens to this tool? It tips off, which is problematic, and we always don't want that. So this, my work, is actually focusing on how well do we know it, which is actually the second tool, in terms of the quality. But I want to emphasize here that it is only addressing the uncertainty part of that quality, but we are not addressing your feature detection or coverage. So what I'm saying is, essence is that bathymetry must carry appropriate and accurate quality metrics. And they are usually, these quality metrics are defined by IHO, that is the International Hydrographic Organization. Or these metrics sometimes also are defined by the nation's hydrographic offices. For example, that's the Office of Coast Survey, like NOAA Office of Coast Survey, for the United States. So they are responsible for defining some of these quality metrics. And because of that, I'll just quickly, briefly review some of the important standards and quality frameworks that is relevant to this work. The first one is the IHO S44 surveys order, which actually defines the survey requirement in terms of the depth accuracy, feature detection, and bathymetric coverage. And I want to say that the most important part of this table that I'm kind of showing us is the TVU, which is the total vertical uncertainty. Because in my work, for us to estimate what I'm calling the interpolation aware TVU, we need to understand the TVU of the measured depth itself. And that is usually calculated using this formula that is shown below, where A there represents the depth independent component, the B represents the depth dependent component, and D itself is the depth. So this is the formula we use to compute the TVU. The next standard that is important that is relevant to this work is CATSOC, which is Category Zone of Confidence. And the CATSOC, Larry and Andy's coming in. Thank you.
Sorry, the late guys.
It's okay. As I was saying, the CATSOC is the Category Zone of Confidence, and this is what is used to define like the uncertainty in the data, and what is the confidence, the quality of the bathymetry to the mariners, and generally the users of this chart product. But I want to emphasize here that if we are dealing with interpolation uncertainty, what that means is that the highest category, the highest level of CATSOC that we can achieve is level B, unless the feature detection part of the feature detection requirement is being met by maybe using side scan. So usually, when you call I'm talking about skunk-striping, when you combine multibeam or single beam and a side scan. So that is when you can achieve like level A1 or A2. But if you are just depending on the interpolation uncertainty that we'll be estimating in this work, then the highest level that you can achieve is level B, because this is usually something I get a lot of questions about. So that's why I'm trying to address this beforehand. Then the last quality metric that we'll be looking at is the NOAA Office of Coast Survey Quality Framework, and this is loosely aligned with the IHOS 44 order and the CATSOC that I mentioned. And why this is also important is one of the goals of this work is to address the uncertainty, the interpolation uncertainty in the MPS project. So that is why this is relevant to this work. So having said all of this, who actually cares about this interpolation uncertainty and even quality metrics I've been talking about? Of course, the mariners, they care because this is important for safety of navigation. Environmental scientists and regulators also care because they need accurate depth and interpolation, the uncertainty information to study benthic habitats. Coastal engineers and planners also rely on this information to build resilient coast. Government agencies such as NOAA, they use uncertainty information to prioritize where they should be mapping, and also for products, for supporting products like the MBS. Insurance companies, they probably care the most because as we all know, money is involved, so they are usually very careful. Hydrographic survey companies also care, and etc. So in this work, I'm proposing 3 interconnected chapters. The first chapter focuses on the estimation of interpolation uncertainty in bathymetry. The second chapter focuses on integration of this interpolation uncertainty and measurement uncertainty for hydrographic quality classification. The third chapter focuses on the application of interpolation aware uncertainty. How do we use this information to plan hydrographic survey? How do we make hydrographic survey design adaptive? And I would get into the details of what I mean by that soon. So let's dive into the first chapter, which is the estimation of interpolation uncertainty in bathymetry. The primary motivation of this chapter is that while methods for quantifying the uncertainty in depth measurements are well researched and developed, quantifying interpolation uncertainty in DBMs remains a long-standing challenge. And when I say remains a long-standing challenge, and it's because there has been previous efforts on methods that have been investigated to try to solve this problem. including trying to use Monte Carlo simulation, using the Krugman approach, Bayesian networks, regression analysis, and more recently, like even myself, doing my master's machine learning approaches. Why we've learned, from all of these methods, like in terms of like how we estimate interpolation or certainty, these studies, we've learned from them, but no one method has become the dominant operational solution to this problem. And that is why we are all here today still talking about this problem. So based on some of the limitations and lessons we've learned from the previous work, the central research question of this chapter is, how well can spectral and spatial statistical methods, which are new methods that we are trying to use, how well can these methods be used to quantify interpolation uncertainty in systematically sampled bathymetric surveys, with the ultimate goal of developing an algorithm that reliably estimates the interpolation error. And when I say systematically sampled, I think that's highlighted. I mean surveys that are not random, surveys that have adequately captured the seafloor morphology. That's what I mean by the systematically sampled. And the conceptual framework of this chapter is really based on these ideas. One is that interpolation error can be modeled as a stochastic process and can also be characterized using nearby observations. We are also assuming that seafloor statistical properties are locally consistent over short spatial scales, which is consistent with the Tobler's first law of geography. And that law states that everything is related to everything else, but near things are more related than distant things. And also, we are also assuming that seafloor statistics exhibit local second-order stationarity and limited directional dependence over short spatial scales. So if we combine all of these assumptions and hypotheses together, we are investigating spectral and spatial statistical methods to estimate interpolation uncertainty. So let's talk about the spectral method first, which is using a spectral analysis to decompose the spatial signal. In our case here, bathymetry into its frequency components, and this power and the power spectral density describes how variance is distributed across these spatial frequencies. So in this framework, what this means is that the power spectral density represents the contribution of the different spatial scales to seafloor variability. And we know that interpolation uncertainty arises from the unresolved variability across the gaps. So if you want to estimate the interpolation uncertainty, the way to do this is to integrate the power spectral density across these spatial frequencies and weight it using a distance-dependent kernel so that we can estimate the variability that propagates over the interpolation distance. And the resulting quantity that we get from this is a scale-dependent estimate of the expected interpolation uncertainty. So that's the first method, which is being done in the frequency space. Now, the second method that we are exploring is the spatial statistical method, which directly measures, try to estimate the interpolation uncertainty in the spatial domain using sliding windows. And the size of the window is related to the interpolation gap, the interpolation distance, in order to ensure scale consistency. So what we are really doing is within each window, we compute the range statistics in order to quantify the local seafloor variability. And across these the windows, we can summarize the range values using what I'm calling the spatial average range, which is taking the mean of all the range values, or the second one here is the spatial envelope range, which is taking the spatial average range plus 1 times the standard deviation. So that's the mean plus 1 times the standard deviation. And the third one here, the third estimator, is the spatial maximum range, which is actually looking at the maximum of all the range values. So to put all of these interpolation uncertainty estimators together, from the spectral framework, we've developed the power spectral density estimator. Then from the spatial statistical method, we've developed the spatial average range, the spatial envelope range, and the spatial maximum range. And we've put all these estimators together into a framework that we called iBlue, which is interpolated bathymetry linear uncertainty estimator. Now, we have all of these 4 estimators. So how do we select the best method? Like, we've developed this, we are exploring, trying to see which one is the best. The first step to selecting the best method is using a safety filter. And we define a metric for that, which is the pass coverage. And what the pass coverage is actually measuring is how well does the estimated interpolation uncertainty that we've estimated using these methods, how well do they bound, or do they estimate the interpolation residual itself? And because I'm saying like safety filtering. So what this means is that any estimator that has a pass coverage less than 90% will eliminate that, and it does not move to the next stage. Using 90%, this is a value, this is a threshold that we would look at more in the second chapter in terms of what exactly is the ideal threshold that we should be using. Should it be 95%? Should it be 90%? Should it be 85%? What is the ideal threshold, the ideal pass coverage threshold? Like that would talk more about in the second chapter. So once we've eliminated the methods that does not meet this minimum requirement, then the next step is using evaluating the remaining methods using statistical performance. Using, when I mean statistical performance, looking at the root mean squared error, the bias, and penalty for underestimation and overestimation. Because we are trying to estimate interpolation error, we don't want to underestimate, and at the same time, we don't also want to overestimate. So we penalize if the estimator is underestimating, and also penalize when it's overestimating. So we need a balance between the two. And putting all of these metrics together, we define what it's called the weighted composite score, which is, so the estimator with the highest composite score becomes the winner, becomes the best method. So that's how we are selecting the best method. So to put this into more context, let's look at some of the test beds that we've evaluated the developed methods. The first, and this test bed, I should say, they've been selected based on different seafloor morphology, different depth ranges, and geographic locations. So the first one is located in the Gulf of Mexico, and it's a low relief morphology with depth ranging from about 26 to 52 meters. And the TVU value for that test bed also ranges from about 0.2 to 0.8 meters. And the source of the data also comes from about 5 different surveys. The TVU and the source of the data will become more important in chapter 2 when I'm discussing how do we integrate the interpolation uncertainty with the measurement uncertainty to inform hydrographic quality classification. But for the case in chapter 1, what we are really dealing with is testbed 1, and I will just show you soon. I will show you all the testbed that we are looking at. So that's testbed 1 in the Gulf of Mexico. Testbed 2 is located in the Florida main channel with depth ranging from about 17 to 28 meters. I also have the TV because of the interest of time. I will just that is not important for at this moment. So we have the TVU and we have the source of the data, which is about also from 5 different sources. Then testbed 3 is located in the Massachusetts Bay, ranging from about 60 to 200 meters. Also, this is the TVU of that testbed, and with two different sources. Then the final testbed is located in the Gulf of Maine with depth ranging from about 20 to 20 meters, with the TVU also ranging from about 0.2 to 1.2 meters, and the survey is largely from 2 data sources. So to kind of, because I showed you so many surfaces, but to kind of like, let just the test beds sink in terms of the depth surfaces alone, and kind of like maybe appreciating like the different seafloor morphologies that we've considered. So this is why I'm just putting this slide there. So testbed 1, testbed 2, 3, and 4 with different seafloor morphology and depth ranges. So now, how do we put all of this? I've described like the methods that we are using, the test beds, then how are we selecting the best method? So what I want to really do here is like, how do we use all of these things that we've developed? So the idea is we take a complete coverage multibeam echo sounder data set that I just showed you now, and we simulate a set line spacing from that using some line spacing. And the line spacing, we've selected them to range from 2 to 6 times the average depth in the area. So we use that line spacing to select the main line, and the remaining data set becomes the validation data set to really test the interpolation uncertainty that we've estimated. So once we've selected those main lines, we interpolate the main lines using, and I want to be clear that we are using linear interpolation, and simply because it is computationally efficient, it is deterministic, and it does not introduce additional smoothing into the data. So once we interpolate the mainline data set, then it's easy for us to calculate what the true residual is by subtracting what the complete surface is, the complete coverage surface from the interpolated surface. So that true residual is really what we are trying to estimate. That is known here because we are taking advantage of a full coverage data set. But in real life, we won't have like the luxury to this validation data set. So from the main line that we've selected, we estimate the interpolation uncertainty using the developed methods that I've described, the spectral and the spatial statistical method. And I want to clarify again that the true residual is different from the interpolation uncertainty. So the true residual is the interpolation error, and the estimated interpolation uncertainty is our attempt to estimate the interpolation residual, if that's not confusing. So again, the true residual is the interpolation error, and the estimated interpolation uncertainty is our attempt to estimate that true residual or interpolation error. So once we do that, then we can evaluate the performance and determine which one is the best estimator based on the weighted composite score that was describing, I just described. So all of these I've kind of like been talking about them, but let's really look at the result, look at some visuals to drive home the point. So, and I will just be showing you, because of the interest of time, I'll be showing you testbed 1 result, and I'll summarize the remaining testbed. So I'm going to go into look at the testbed 1 result in detail, and I will summarize the remaining testbed. Like I said, the different line spacing that we are evaluating is based on 2 to 6 times the average data depth. So for testbed 1, the average depth is 42 meters, and we are looking at all of the listed line spacing. And for the sake of this example, I'm just going to take the 128 meters line spacing to show you what I'm talking about, how the workflow is, what the workflow is doing. So we take the complete coverage data set. We simulate that, we simulate a set line spacing survey from that using 128 meters line spacing. From that sampled data set, we interpolate that using linear interpolation. Then we get what the true residual is by subtracting the complete coverage by subtracting the linear interpolated surface from the complete coverage surface to get the true residual. And this true residual is our target. That is what we are trying to estimate. So the true residual again, and using the methods that we've developed, that's the PSD uncertainty is coming from the spectral method, and the SAR, which is the spatial average range, is coming from the spatial statistical method, and also the spatial envelope range is also coming from the spatial statistical method. And if you look at compare the true residual and those surfaces, you see the same pattern in them, but maybe that is not even clear enough, because maybe there are some outliers acting on the true surface itself. But if we subtract the true residual, like the estimated surfaces from the estimated uncertainty surfaces from the true residual surface, the difference is what I'm showing down here. Am I covering? Okay, yeah. The difference is what I'm showing down here. So this is what we get from the PSD method. This is from the SAR estimator, then from the SAR estimator. SAR is the spatial average range. SAR is the spatial envelope range. And if you look at it, everything kind of like falls within like the zero domain. Although like, you can maybe see some things going on here. And that is inherited from the original data set itself, which also like maybe like drives home an important point that like the quality of the data that you also use also affects your interpolation, how you estimate your interpolation uncertainty. So to look at maybe this the surfaces more closely, if we take a profile across the test bed, so the residual itself is the one in blue, that is what we are really targeting, and what we've estimated, that's the PSD is the one in orange, the SAR is the one in green, and the SER is the one in red. And you can see like the most of the methods, like they bound the residual, but the PSD like maybe like it's tighter compared to the other methods, which they tend to be more conservative and overestimate the uncertainty. But that also maybe goes back to the point of like which estimator is the best in terms of like that is safe for navigation and is also efficient in terms of survey efficiency. As we know in hydrography, that the tail of the distribution is very important, because that is what causes the maritime accident that we have. So like those cause navigation risk. So like I examined the tail of the distribution by using what I'm calling the normalized residual distribution. So what that in essence is scaling the true residual by the uncertainty. And if the uncertainty model, if they are perfectly calibrated, what we should have is a standard normal distribution with a mean of 0 and a standard deviation of variance of 1. So for the PSD, the curve there, the one in blue, if we look at it, it's called the leptocortic, like the shape of this distribution is called the leptocortic distribution. But what that means is that it has a peak top, and it is heavily detailed. The tail is heavy. So, but this is like maybe one might feel like, this is concerning. But in essence, what the most important result from this is that our estimators estimating the true residual, like are they underestimating, or are they not underestimating, which is really what is concerning, which the answer is no, and we'll see that more in detail now. So if I move on to the next, if I show us, what I'm trying to show here is if the white is kind of like saying no, and what this is saying is the normalized residual greater than 3, and that is what the leptocortic distribution means. So if you look at all the places that we have red, you can see that they are very small, like they are very small. What I'm really trying to drive home with this point is that the estimators are doing well. Maybe this will also help to clarify that point in the sense that if you look at the past coverage, the SER, which is the spatial envelope range, estimate the past coverage of that is about 98%, and for the PSD, which is the spectral method, estimated about like 95%, and for the spectral average range, estimated about the past coverage of that is about 93%. And remember, like I said, the threshold that we're using is 90%. So what that means is that all of the 3 methods, pass the first stage, of how we are selecting the best estimator. So what's going to decide the best method now is using like how calibrated they are in terms of statistics, in terms of like, when we look at the root mean squared error, the bias, and overestimation and underestimation. And if we do that, the PSD becomes the winner for this line spacing and on this test bed. So to kind of like, I showed you just 128 meters line spacing, but all the remaining line spacing, like the best estimator, like, you kind of like see them like from 80 to like, about 1 kilometer. And the dominant, the overall best estimator is the power spectral density for this test bed. So we could also look at the remaining test beds. I promised to summarize the remaining test bed. So test bed 1, like that's the power spectral density. You can see it in purple. Then the spectral envelope range kind of like dominated on test bed 2, which is in orange. Then on test bed 3, like the spatial average range dominated, and on test bed 4, the spectral envelope range also dominated. And why this is happening is really because of the complexity of the test bed. So the more complex the test bed is, like, the spectral envelope range tends to, like, handle that well. But like when the test bed is relatively of low morphology, for example, like test bed 1, that's why the power spectral density kind of like works well. But I want to also emphasize here that it does not mean that the power spectral density does not work well at all on the remaining test bed. It's just that statistically, the other methods, like, perform better. So, this concludes the chapter 1 of this work, which, like, as you can see, has mostly been done. And as we can see that, okay, now we are estimating at least we are reliably estimating the interpolation uncertainty. So what do we do with this information? And that takes us to chapter 2, which is all about integrating the interpolation uncertainty with the measurement uncertainty for hydrographic quality classification. Now is when we want to start to talk about what level of cutoff do we meet based on what I'm calling the interpolated aware total vertical uncertainty, and I'll get into that in a moment. So the motivation for chapter 2 is why uncertainty measurement is typically well characterized using like the total propagated uncertainty models, TPU, like we all know that. Interpolation uncertainty remains loosely integrated into hydrographic quality framework or classification workflows. And what I'm really trying to show here, this is from now post, the measured depth, I'm talking about the image, this image here, the measured, where is it? Okay, yeah. The measured depth is in cyan color, and this is what we've interpolated. This is what has been interpolated. You can see there is a lot of interpolation going on. And this is the uncertainty surface. So like I took it just from now post, Glenn, and I think the interpolation uncertainty here, it's maybe kind of arbitrary the way it's been defined now. Glenn, right? So yeah. So that is the essence of this work, like, so that we can have more confidence in the uncertainty in those areas that we've interpolated. So that is the essence of the motivation for this chapter 2. And with the research question that we are trying to answer with this is, how can interpolation uncertainty be integrated with the model TVU, which I'm going to get to in a moment, and the slope-induced uncertainty to support hydrographic quality classification within the interpolated bathymetric regions, with the goal to develop an interpolation-aware TVU framework. So the conceptual framework, the main idea for this chapter is, the first thing is, what are the components that drives the interpolation-aware TVU? The first one is the interpolation, the uncertainty associated with the depth measurements that was used for interpolation itself, one. The second one is the uncertainty that's been introduced through the interpolation process, which is what the chapter 1 was all about. Then the third one is the slope-induced uncertainty introduced by horizontal positioning error. And I've tried to describe what I mean by the slope-induced uncertainty introduced by the horizontal positioning error with the diagram down below. On the flat seafloor, like if you have any form of like TVU, that does not it does not propagate into the vertical error. Like your horizontal uncertainty does not propagate into the vertical error, or vertical uncertainty or error. But on the sloped seafloor, it's easy. When you have horizontal position error, that is easy to propagate into a vertical error, which I tried to show here. So this is exactly what I'm describing. This surface is sloped, and this is the TVU that is going on. This is the point that we interpolated. So that what that means is that we also contribute this vertical error. But in the case of here, it's relatively flat. So the interpolate, we don't have, it's kind of like same depth, and we don't have any vertical error. So that is what that slope induced uncertainty is really trying to trying to estimate. So in case we fall in this kind of case, would this be significant or not? Yeah, that's also another question that we would see as I address this problem. So once we have these three components, the next step is let's put everything together, so integrate these three components to obtain the interpolation aware TVU. So combining the model TVU, the interpolation uncertainty itself, and the slope induced uncertainty. So once we have this information, then we can assign hydrographic quality to the interpolated region by comparing with the cutoff level that what we've estimated meets. Excuse me. Let me. So let's look at the methods that I'm proposing for how I want to do this. The first one, which is the first component, is how do we represent the total vertical uncertainty for the interpolated regions. I'm proposing to use the which I'm proposing, which I've also maybe done some part of this work too, is to use non-linear least square methods to estimate the A and B. And when I mean A and B now, based on the IHO model for TVU, which is the square root of A squared plus BD squared. So the idea is we have the TVU that I was showing on the test bed. We have the TVU for the test bed, and we know what the depth is. So can we estimate the A and B using that information with non-linear least square method? And what that will allow us to do is to estimate the measurement, the total vertical uncertainty in the interpolated region. This will become clearer soon. The other approach that we are also investigating is can we just even interpolate the TVU itself? So what I'm saying is, for example, if this is our sample data set, like I'm showing there at the upper right corner, if that is the sample TVU, that could be the sample TVU or the depth. So we know the depth and we know the TVU. So if we plot that in terms of the depth and the TVU, this is what that looks like. And the idea is we want to fit a non-linear least square method, which it's the Leffenberg-Marquardt algorithm. Don't worry about the name, but it's just a way of fitting a non-linear least square in to your data. But as you can see, like maybe the data is a bit noisy. So the first step before we fit the nonlinear least square method to the data itself is to try to clean up the data by bending the data or like using like the kernel density estimation to kind of like to smoothen the data before we estimate what the A and B is. A again is the depth independent component of the TVU, and B is a depth dependent component of the TVU. And this is the result here, like the estimated A for you when we use the bending method, and they're almost the same, 0.324 and 0.235, and with B of like 0.002. So if we try to use this information, this A and B now, to fill in the gaps that we have up there. this is what that will look like. The original TVU, I'm just kind of like showing us so that we can compare what the estimated looks like compared to the original. So the original TVU is the one, like the one on the left. Then the Bainin plus the nonlinear least square method, that's what is been estimated. Then the kernel distance, the kernel estimation plus the nonlinear least square method is what we have, like at far right. So if we try to just interpolate that, like what we get, like interpolate what I'm showing up here. I think I'm covering it. Yeah, what we interpolate this, what we get, is it better? So looking at the result, this is what when we use like the nonlinear least square method to estimate A and B, this is what we get, and this is when we just interpolate the TVU itself. And this is the difference between the between the three methods that we try. So like this is like preliminary results, like I just started like maybe getting into this, so like, but I just thought like maybe this is cool to kind of like to show. So that is the first part of the component that we need to obtain our ITVU model. ITVU is interpolated aware total vertical uncertainty. So the interpolation uncertainty estimation itself, that has been done from chapter 1. So we just grab that information plus what we've estimated the TVU representation for the interpolated region, then plus the slope induced effect that I was talking about. And for us to do that, for us to estimate the slope induced effect, what we need is first the estimation of the slope from the measured depth, then the estimation of the total horizontal uncertainty, like for the measured depth, and then propagate those two together by like multiplying them. What the right propagation model to, like it's this is what I'm proposing. We might eventually use this, and it might be something else, but like this is what I'm proposing, because I've not gotten much into this, so don't take me on this. Then the next thing is to combine these components together, like using like law of propagation of variance, and with the assumption that like these parameters are independent. So once we have that, then we can assign the quality, the hydrographic quality to within the interpolated region. And how do we evaluate like what we've like this estimation? First is like we need to look at the agreement between the estimated TVU and the reference TVU, which I was kind of like, which I just showed you, like the difference between what we estimated by the three different methods, the Bainin and the nonlinear least square method, the KDE and the nonlinear least square method, and the interpolation. So which one is the right one to use? That's the first one, the first evaluation framework. The second one is how appropriate is the proposed ITVU model that I was just saying, like in terms of the propagation of that is based on the propagation of variance. Then the next one is the correctness of the interpolation aware like hydrographic quality classification. How good is this? Then this final point I think is important because I kind of like mentioned it from the beginning, which is the assessment of the pass coverage threshold, like which one is the right coverage to use. Because a lower pass threshold, like may be more optimistic in terms of like our hydrographic classification, but that might increase our risk. But if it's higher threshold, that would improve the confidence that we have in our uncertainty estimation. But that might be at the expense of the survey efficiency, without kind of like, which is my chapter 3, which I will get to in a moment. And so identifying what the appropriate pass threshold like is, it kind of, you need to balance, navigation or uncertainty, then operational practicality to like, we need to kind of like, balance those. Then finally, chapter 3, like, tries to take the information that that we get from chapter 1 and chapter 2 and try to, take this further and like, applying it to adaptive hydrographic survey design. And what do I mean by this? Currently, like, we use set line spacing a lot, like especially in the United States, which like, which is good, like, it's what we can do. But like the way the set line spacing survey decisions are made are largely subjective, and it's maybe based on like, rule of thumb or like, operational constraint. Like, so there is no any objective maybe framework that drives how we set the set lines that we use. So that's the motivation. And the research question that I'm really trying to answer is like, how well can the interpolation aware total vertical uncertainty that we got from chapter 2 support near real-time adaptive hydrographic survey design while satisfying like the uncertainty requirements and maintaining survey efficiency? So balancing, making sure that we are meeting the requirement and also making sure that we are maximizing like the survey, like setting the line spacing. If I'm supposed to set it, for example, maybe 50 meters, can I still take it to 100 meters and I still meet my requirement? Like, so that's again, or do I need to reduce it? So like, making sure that we just don't go to the field. And for example, the demonstration that I have here is what that is exactly saying that on this floor that is relatively flat, our line spacing is spaced. And when we have something like this, like a more of a rugged seafloor, then we bring it closer. But if we've done this, we will not. This is the motivation. Like I went back in slide. So if we've just set a constant line spacing, yeah, it maybe still works, but like we can be more efficient if we use the interpolation aware uncertainty information to to plan the survey. So, and the goal of these two is to develop an adaptive hydrographic survey design methodology. And the framework for this is really based on the idea that the interpolation aware TVU can be modeled as a function of distance from previous survey lines. Then the maximum survey interpolation uncertainty between adjacent survey lines is statistically like at the maximum between those two lines. Then the third really idea is that the weight of the ITVU code, it really depends on the statistical characteristics of the surrounding seafloor. So the way this is going to work is the initial, so we go out there in the field, we acquire the initial line, and from that initial line, we can estimate the ITVU growth curve. And from that ITVU growth curve, we can determine what the maximum our line spacing should be for us to meet our spec. And we do that with we can acquire the next line and the process repeats. And how are we going to evaluate this? First is that it's going to be a form of retrospective evaluation using simulated survey scenarios generated from the testbed that I was showing us earlier. And the performance will be compared with the fixed spacing survey strategies that we currently use by looking at compliance with the prescribed cutoff or NOAA uncertainty threshold that we want to meet, or what is the survey line density reduction that we get, or what is the do we gain some time in terms of do we gain some time by using this framework, and what is the overall data collection efficiency? And since I'm trying to say that we can use this near real time, we also need to be thinking about the computational performance of this framework. And what we expect to get from this is an adaptive hydrographic survey design planning tool. So going from this to this, from this is what you be to to be to have an objective way of determining what the line spacing should be. So that's kind of all the three chapters, and I would just want to highlight some of the potential scientific contributions of this work. First is the quantification of interpolation uncertainty using spectral and spatial statistical methods. Then development of the ITVU framework for digital bathymetric models and hydrographic quality assessment. Then development of an uncertainty-informed framework for adaptive hydrographic survey design, and putting all of this together into a unified operational framework for uncertainty estimation, integration, and uncertainty-aware survey design in bathymetry. And the potential operational deliverables I'm hoping to get out of this work is iBlue, which is an interpolation uncertainty estimation algorithm, then the ITVU quality classification framework, then IHydro planner, which is what I'm kind of calling interpolation aware hydrographic survey planning framework. So those are the three operational frameworks I'm hoping to get from chapter 1, 2, and 3. And what is the significance of this work? I think one, it will enable us to accurately estimate interpolation uncertainty in digital bathymetric models. For example, the National Bathymetric Source. It would give us greater confidence in bathymetric products for different applications. Then it will improve like our chart accuracy. It will help us to optimize hydrographic survey design. It will also improve hydrographic health modeling. And this matters, like, this is important to all of these organizations from NOAA to like ISO itself, then hopefully hydrographic offices, companies, and vendors. And this is the timeline, like, so these are the major milestones, like, trying to complete my dissertation, like, and hoping that next summer, hopefully, like, I'll be defending this. And I would like to acknowledge everyone. It's a long list, but I think you all deserve it. And for my advisors, Kim and Christos, to my committee members, Glenn, Key, and Larry, and my NOAA collaborators, which again, Glenn is coming back, Francis and Katrina, Brian, and Andy, then like all the CCOM faculty, Val, thank you everyone, like I always speak your brain. And CCOM IT and admin and Colleen, everyone has been wonderful. Then Sanam, Key introduced me to Sanam, like he also helped like with some of the statistical analysis that I've done. All my UNH friends, mentors, Pete, he has always been there. Nigerian family in the US, friends and family back home. And of course, like I like to acknowledge what is like supporting this work, the NOAA award. Then the scholarships I've gotten from like THSO, MTS, SUT. Thank you everyone. And of course, last but not the least, my darling wife and my adorable son, they've been a big part of this journey. These are my references. Thank you everyone.
All right, so we have time for a few questions. As I said, the committee members will wait, although Larry, I know that your time is potentially limited, so we'll make an exception for you. So questions from anyone?
Katrina.
I had a question for you for how you were choosing your test beds. I noticed some had 2 sources or some had 5 sources. I understand picking different types of seafloor geomorphology, but did you look to see if they had like complete bathymetric coverage, or were some of those test beds also including interpolated data? And were those multiple sources from different dates? Like, did you look at any of the range of dates from the areas?
Yeah, thank you. The first question, all of the data set are complete coverage data set, no interpolation, because it will not make sense. If we are trying to estimate interpolation uncertainty and we are using data that has already been interpolated, so I think that is really wrong. So that's for that. For the second question, which really based on this the sources, I've not looked at in terms of where are they coming from, but I was discussing this with Glenn. Like this work, I kind of like just completed it last week, and so I was discussing with Glenn last week, like the way I was getting my source from the third band of like the blue topo, and like so for now I'm just kind of like plotting what I'm getting, but I need to go back to maybe to be able to trace where is this survey coming from and what is the cat sock that survey is meeting. So that's something that's been done, and also, Christos also mentioned this during our meeting too. So yeah, so it's something that I'm thinking about, but I've not just gotten there yet.
Yeah.
Who do I go first? I'll come to you. Pete, let's go for Pete.
Elias, great job. Really, really enjoyed your presentation. I just have one question and one suggestion. The question is a very basic one. What are the size of your test beds, and did you select uniform sizes for all your test beds?
Yes, the size is 10 kilometer by 10 kilometer, and everything is the same size. Yeah.
Okay, good to hear that. Second point is a suggestion. Between your introduction and chapter 1, move the test bed information into that.
Okay.
Doesn't work very well the way you have it at the moment. A description of the test beds and how you got there, and then your current chapter 1 will become chapter 2. Just a suggestion.
Yeah, thank you for that. Yeah, thank you.
But great job.
I appreciate the suggestion. I think Val, Ellie will come to you. Val, go ahead.
We go back to your slope uncertainty estimation slide.
That's a good one. Maybe I should just do this. No, hold on. Okay, yeah. There we go.
Yeah. This is a great slide because I think it illustrates what you're trying to do really well. But my question is, it seems to me that you pick the position for where you're going to interpolate. And so there's no horizontal uncertainty in that. And I wonder if what you're really trying to do here is estimate the uncertainty of the interpolated place due to a miscalculation in the slope, due to uncertainty about the horizontal position of the places you did measure.
Yes, it's the second one, the horizontal uncertainty in the measured depth itself.
So in this drawing where you have horizontal uncertainty at the interpolated depth, you should really, that's really a result of, it's really the horizontal uncertainty at the measured depth points and then a resulting slope error. Is that, do I understand?
Yeah, like this, I was trying to explain this to, I think, Glenn too, and he was not really able to follow me, so I needed to try to make this like slide, and hopefully it helped. But yeah, I know it's a concept that's not easily like, maybe that's kind of like.
It's a really important point because the grid node itself has no horizontal uncertainty.
Yes, no, it does not. Yes, it does
So you
not.
could like, in your drawing on the right, for the measured depth on the left-hand side, you could move that, say, for example, further to the left, and that would give you a flatter estimate of the slope, and that would better illustrate the effect, I think, that you're trying to show there.
Okay, yeah. Thank you.
But Cube does propagate the horizontal uncertainty associated with contributing measurements to a vertical uncertainty.
That's true, but isn't it true that you're not doing interpolation from cube estimates, you're doing it from soundings? Is that correct?
Well, that's an interesting question.
Yeah, that is an interesting question, and yeah, like this is something that like we've not discussed. I think in our meeting too, like it came and Chris to it's something that like we really need to like figure out like how we going to approach this, because Cube does not give like the horizontal on the THU. So we go back to the source data to get it, or is there a way to get it, a different way to get it? So that's what I've been kind of like, maybe it's been giving me sleepless night, like, because that's a major part of
Cube
like.
does incorporate the horizontal uncertainty into the vertical uncertainty.
But like what I'm saying is for the measured depth itself, like the total horizontal uncertainty to have that independent of the CVU. That's what I'm really trying to say.
Doesn't exist.
It does not exist. So yeah,
Because it's been propagated, the vertical has been inflated to accommodate the horizontal.
Yeah, and originally too much.
So that's or maybe brings up an important point. Like, is this going to be how much this slope induced uncertainty? Like, how important is that to like the ITVU model I'm talking about, or like maybe I'm just the one thinking too much? So like, please, if you have ideas.
I think the key is the slope issue is the key issue.
Yes.
And I think you're getting a little misdirected by thinking about the horizontal uncertainty, because if it's a cube measurement, that's been incorporated into the TVU, but that doesn't account for the fact that you don't know the slope between the grid nodes, and that's going to have a huge impact. So I think it's just a semantic issue, really.
Yeah. I'm happy to follow up on this.
Cube value wouldn't apply in the set line spacing to the extent that it would in the full data set. So if you're just looking at set line spacing, you don't have a model to build the uncertainty. It only comes from the soundings, right?
Yeah. Yes.
So because my question is relevant to, I think, this whole discussion, and it has to do with the adaptive survey strategy, which I think is really cool to aspire to. but you really don't know what the slope is where you haven't measured yet.
Yeah.
And so I can't see really a kind of a priori determination of what the optimal next line spacing is going to be. What I could see though is that you go and run your line, and then you run your next standard line, and then you've determined that that's too much, and you have to come back and split the line. So that it could be adaptive in that sense, but you're never going to know what that's, if you haven't surveyed the area yet, you're not going to know what that slope is going to be.
Yeah.
Or maybe do a cross line first.
Well, as long as well, you should do a cross line first, but you don't, they're two-dimensional.
Sure.
Yeah, like, so, I mean, Christos also raised this same point too during our last meeting. Yeah, maybe I'm aspiring. It's an aspiration, but like, I feel like, we can do maybe better than what we currently have in terms of like trying to use like this interpolation uncertainty information to somehow like, inform the set line, the spacing that we choose. But how that exactly is going to be done, yeah, like, it's still subject to exploration. So, but then, yeah, thank you for raising the point. Like,
So is your intention to look at the set line spacing scenario in terms of what you're going to look at, or do you intend to also look at existing profile data, non-full coverage to interpolate to determine uncertainty in existing surveys?
oh yeah, so it's the two, like using the complete coverage, so that we develop this the frameworks. Then, like, use that information to estimate the uncertainty in archived data sets where we don't have that luxury of.
So one thing you have to keep in mind is that the azimuth of the survey lines would be different in a set line spacing scenario with multibeam or side scan than they would have been in existing single beam surveys. So those single beam surveys would have been run perpendicular to the slope. And in a set line spacing, they're probably running parallel to the slope. So you may have a different kind of physiographic environment that you're trying to assess. And so it seems to me you ought to look at dividing up your test bed into lines run in different orientations.
Yes, that's it. Instead of kind of like going maybe north-south, like look at different.
So you'd have a very different situation in your slope if you were running perpendicular to the slope than if you were running parallel to the slope.
For your chapter one, we discussed that previously, and you said that you did, right?
Yeah, like
you tried the traditional, what you showed as the north-south and also perpendicular.
Yeah, it's going to be the same result, like,
Not that for chapter one, but for the other chapters, I agree, it's very important.
I think you'll find also that different Army Corps districts will run in different directions. Some of them will run set line spacing with the channel, and some will run across, so you might have some really good examples just from different districts.
Yeah, I'm happy to talk like Katrina, maybe gets like, maybe good example of like data sets to look at. But I totally agree, like, the direction is also important, but like the way, like, the algorithm and the framework is like, we've developed it can work with any direction. What you just need is give me the depth, give me the distance between the lines, and I can use that information to estimate what the interpolation uncertainty is. So like we thought of like kind of like Glenn, thanks to Glenn.
I'm mindful of time, so let's take one more question.
Yeah, I know Eli has, maybe Kim, if I could plead, Eli and Imo, please.
Okay, two more questions.
Fantastic talk. I just had a quick question about the sort of the dreams of chapter 3, looking at the dynamic survey line spacing. Have you given additional thought to like what type of seabed morphology, like what that test bed site might look like?
Sorry, have I given what a thought?
Yeah, like what, I guess which, if you have a particular survey area in mind for your dynamic line spacing, work or a particular type of seabed that you wanna dig into with that?
I'm not sure I'm following, like, in terms of the test beds that I want to use for the, evaluating, like, my chapter 3, right? Is that what you are saying? Yeah, like, I mean, for example, an ideal test bed would be something that has like more of like, maybe a relatively flat seafloor, and also something that is also off, so that I can really demonstrate what I was saying by like, you have like maybe wider line spacings where you have like where the seafloor is relatively flat, and like, as you go into like, more of a rugged seafloor or a complex seafloor, then you try to bring your line spacings together, if that answers your question. Yeah, but Eddie, don't worry, you can definitely talk.
I know where you're,
Imo?
Yeah, well done, Elias. So the question I have is, I was trying to determine what you mean. What's the extent of your slope? Does it mean from one end, one line to the next one, or does it mean given the type of seafloor morphology you try to scale out? What's the grade that you consider significant? So let's say you have something that's with a grade of nearly 0. Does that count into what you're trying to estimate?
So when you have like, thank you, Imo. When you have like a relatively flat seafloor, like, your slope becomes 0, and that's what I was, maybe it's here, where I was showing the formula. This becomes 0. So because it's a multiplicative factor, so that becomes 0 and it does not count. But if the slope is significant, just like you are saying, then like it counts, and the slope is measured from the depths that you are using to interpolate. They are not the slope of the seafloor itself.
Thank you.
All right, well, thank you, everyone. Very much appreciate the questions and your presence. So the committee now, we have the Brennan reserved. I think that's probably better than a big meeting like this. So thank you very much, and thank you, Elias.